Welcome to our presentation. Today we are going to present our paper titled CADUE, Content Agnostic Detection of Unwanted Emails for Enterprise Security. It's a joint work between QCRI, Qatar Computing Research Institute, and Stevens Institute of Technology. And this is the lineup of my talk. Initially, I'll give you a brief introduction to the problem we are addressing and provide an overview of our approach, followed by how we collect data and perform feature engineering to train machine learning models, and briefly touching on key experimental results before concluding the presentation. Let me give you the motivation behind this work. Existing approaches rely heavily on header and content to filter unwanted emails. When we say unwanted emails, these are mainly spam and phishing emails. But due to the increased utilization of end-to-end encryption and due to organizational policies, the content of the emails are increasingly not available to security appliance to make this judgment. We observe that existing approach fail to perform well when the content is turned off. The key goal of this work is to come up with a way that works well without utilizing the content. The prior work can be divided mainly into two groups: content-based approaches and content-agnostic approaches. As you probably have guessed, content-based approaches utilize features extracted from the content. And I have listed two main work in this area. One of them, for example, malicious URLs by Ho et al. They identify the URLs inside the message bodies. And based on the reputation of these URLs, they make a judgment as to whether these are spear phishing emails or not. Verma et al., on the other hand, looked at the textual pattern utilizing NLP to decide whether it's a phishing email or not. And from the content agnostic approaches, where they only use header features to decide whether it's an unwanted email, SNARE is one of the very early work where they try to profile senders to identify unwanted emails. But their approach only applies to spam emails, and also the accuracy is quite low, in the range of 90%. And recently, Gascon et al. Profiled senders and the email composition features in order to identify unwanted email. In their approach, key limitation is it's only applicable to spoofed sender emails, but in our work, we try to address a wide range of unwanted emails. Not having access to the content makes it hard to distinguish benign emails from unwanted ones. And on top of that, existing content agnostic features are not robust. They are easy to be changed by attackers to fool the detection models out there. And our key intuitions and observations to improve these are as follows. One key aspect we notice is most of the existing phishing detection systems treat each email independently. In other words, they don't take the context information into account. And also, we noticed that enterprise email patterns can reliably identify benign communication patterns. And if we know the benign patterns, we can distinguish them from the unwanted ones. So in short, we take historical enterprise email communication patterns as context information to solve the problem. The two diagrams in this figure shows the degree distribution for two graphs we built based on the email communication patterns in the enterprise. In a later slide, I will be explaining how we build these graphs. A key point that I want to emphasize here is the shape of the distribution. They closely follow the power law distribution, which is atypical in a social network. And also, based on our community detection analysis, we identified clear communities in these two graphs. And you can think these communication patterns form a social network, which we call email social network, that can help us to distinguish between benign communication pattern from the malicious ones. This diagram shows a typical enterprise email architecture where external emails first go through firewall and then through a security appliance which scans these messages to determine whether they are unwanted or not, and then pass it to the Exchange server before they reach the user's inbox. And in this work, we assume that we have access to the server logs, internal server logs of the Exchange server. Typical email consists of a message header and a message body, and they predominantly use the SMTP protocol. In this work, we assume that we have access to the header, but not to the body. And when I say body, it includes the attachments too. And also another important thing is when we derive these features, we only relied on commonly available header features and did not use any of the headers that are added by security appliances or other third parties. This diagram shows the overall approach we take to detect unwanted emails. We first collect benign email communications from the internal Exchange server logs, and then identify external emails and internal emails. External emails are those emails sent from external parties to internal users, which cross the firewall boundary. And internal emails are those emails then sent within the organization. Based on the external emails, we build what's called sender profiles. And based on the internal emails, we build enterprise graphs. And we use these profile features to extract sender profile features and also enterprise graph features. We extract sender profiling features from the profiles we build for senders, and enterprise graph features from the graphs that we build from the internal communications, and also header features directly extracted from the email as our feature set. And based on all these features, we train a random forest classifier that can distinguish between unwanted and benign emails. We collected around 588K internal benign emails, and there were roughly 5,500 users, out of which the majority are external users. And from the incoming external emails, we collected 16,310 emails, and out of which most of them are benign. We treat these emails as our ground truth to train and test our model. Now we are going to look at each of these categories of features. First, onto header features. As I mentioned earlier, these are extracted directly from email headers. And in fact, they are adapted from the header features used in Spam Assassin, which is a popular spam filtering software out there. And we make a distinction between regular and enhanced setting features. When we say regular, they include all the commonly used header features in email systems. And in the enhanced setting, we exclude features such as subject, IP, and delivery path from the header features, as some of these features are not available with some of the end-to-end encrypted solutions. And the header features serves as our baseline features to train our baseline model. Sender profile features, they are extracted from emails sent from external users to internal users. They especially help us distinguish spam and phishing emails sent to several users. We perform sender profiling at 3 different granularities: at receiver level, and at receiver and subject level, and at sender and receiver levels. Each of these profiles capture different aspects of the sender. Now moving on to enterprise graph features. Before I show you the features, I would like to give a brief introduction to how we build these graphs. We built 2 graphs, namely co-recipient graph, which captures the co-recipients in emails. So if two users, if an email is sent to 2 users, they will be considered as co-recipients. And the second graph, the sender recipient graph, which is a directed graph, where it captures the associations between sender and the recipients. And for example, the first, let's assume that an email is sent from user V1 to V2, V3, and V4. And this results in the click for the co-recipient graph and this directed graph for the sender recipient graph. So we do the same exercise for all the emails in the benign set and build this huge graph that captures the co-recipient relationship and sender-receiver relationships. Based on these two graphs, we extract graph features, and they capture benign communication patterns in the enterprise. We identified two main feature categories. One set identifies community-based features. For example, if two recipients are from the same working group, and the other set of features identify the relative importance of the users in the email. Based on the features we extracted earlier, we trained a random forest model to detect unwanted emails. These figures shows the ROC curves for different settings. The figure on the left shows the ROC curve for the regular setting where we considered all the commonly available header features. As you can see from the diagram, enterprise features are performing quite well compared to the header features. And combining both enterprise and header features, which we call all, perform slightly better in terms of false positive rates. The figure in the middle shows the ROC curves for enhanced setting where we turn off certain features which may not be available under certain end-to-end encrypted products. And as you can see, enterprise classifier is still performing as before because the features we turned off did not affect the enterprise features. However, the baseline header feature-based classifier was affected greatly because of the enhanced setting. This demonstrates the power of enterprise features and also shows that it can work even with limited header features. And the diagram on the right shows the ROC curve for different epochs, where we train the model for 14 days and then test it on subsequent days, with each having 3 days worth data. It is understandable that the performance of the model degrades with time, but the key takeaway here is the amount of degradation is much smaller, which suggests that our model can work for a long time without being retrained. The diagram at the top shows the top 30 features that our classifier identified. And the green bar shows the enterprise features and the purple bar shows the header features. As you can see, 3 out of top 4 features are related to enterprise features, which demonstrate the importance of those enterprise features over the header features. And we also group these features into the 4 main categories we identify. And an important observation we make here is each of these subcategories are well represented in the overall importance. That makes it difficult for attackers to fool the classifier, as they need to change multiple attributes from multiple categories, which is a difficult task to do. Now let me briefly touch on the limitations of the work, which could help to advance the research in this area. One limitation of this work is the duration of the data set. We only had access to data for 25 days, but we believe we can do much better analysis and fine-tune our models had we had access to a larger, longitudinally larger data set. And also this approach currently applicable only to the enterprise setting, because we rely on the communities that are formed in these enterprises. It may not directly translate to non-enterprise settings. When we profile the internal emails, we assume that the working groups within the enterprise do not change frequently. And if that assumption does not hold, we probably need to come up with techniques to do dynamic profiling. And finally, our model assigns a lower confidence when flagging fresh senders, especially those emails which are sent to single recipient. But if an email is sent to multiple recipients, our co-recipient graph-based features come into rescue and help distinguish between benign and the unwanted. So in conclusion, we showed in this work how to detect unwanted emails in a content agnostic manner, and we leveraged enterprise communication patterns to design discriminating and robust features. These features include sender profile features and enterprise graph features from two key graphs we built, namely sender receiver graph and the co-recipient graph. Overall, our approach achieves a high true positive rate of 95.2 and a low false positive rate of 0.3%. So that concludes my talk. If you have any questions, I would be happy to answer now.